Good morning to all of you. Today we are going to study another very important topic, and that is forced oscillation. Now, before forced oscillations, in our last class, we have studied simple harmonic motion and damped oscillator. So before we go into it, let me quickly revise the formulas and the concepts we have studied. So in the simple harmonic motion, as we see that first of all we have to see what are the forces which are acting. So there is a restoring force F. F is equal to minus kx. So now we write the equation of motion, sigma fx is equal to max. So sigma fx is minus kx mx double dot. That gives rise to the equation of motion x double dot plus omega 0 square x is equal to 0. The solution of this equation is x is equal to a cos omega 0 t plus phi. Now when we are studying all the three together, omega 0 is for the undamped simple harmonic motion. So that is also known as natural frequency. Omega 0 is equal to root over k by m. A is amplitude, energy, and Q factor is infinite. Now, in case of damped oscillator, what we find that obviously the restoring force F is there, but along with that there is another force F, small f, which is basically resisting the motion. So that is a damping force. So that is the proportional to velocity, and it is written as minus bv because it is opposite to that of the velocity. So f is equal to minus kx, small f minus bv. So equation becomes sigma fx minus kx minus bv mx double dot. So x double dot plus gamma x dot plus omega 0 square x is equal to 0. This is the equation for damped harmonic oscillator. Gamma is B by M. So these are the concepts we will need now. Gamma and omega 0, they are the two important parameters. Gamma is a damping constant and omega 0 is an oscillating term. So gamma and omega 0. Xt, the solution of this is xt a e to the power of minus gamma by 2t cos omega 1 t plus phi. So we have defined another omega for the damped oscillator, that is omega 1, and that is omega 0 square minus gamma square by 4. Okay. This is the amplitude. So at is equal to a e to the power of minus gamma by 2 t. E varies as E is equal to E0 e to the power of minus gamma t. The quality factor for the damped oscillation, omega 1 by gamma, which is approximately, if omega 1 is close to omega 0, then omega 1 we can write omega 0 by gamma, which is the quality factor when omega 1 is very close to omega 0. Okay. So now we will study the forced harmonic oscillator. What we need to see actually, that there are large number of internet sites, the books and course materials. So this topic has been dealt in different places. There are many very good videos presently in the internet, and I want you to see them. But what we have to remember, that when we are studying this either simple harmonic or the forced harmonic, what we have to remember is that the fundamental, that we have to see that there are certain fundamental concepts. Like this is a fundamental concept. What we do over here is we write down the force. What are the forces acting on the body? And then we write sigma fx is equal to mx. Then we get the equation of motion. Similarly, there are certain fundamental concepts. So those are the concepts we have to learn. And I have tried to make it as simple as possible so that we only study the fundamental concepts, because rest of the things you can calculate. Alright. So let us take some of the examples of forced harmonic oscillator. One example that is the simplest case, and we are going to study that, is a mass which is attached to a spring in the gravity. So gravity is a constant force basically. So it is a forced oscillation. So there is a constant force, gravity, and the spring, the mass is oscillating attached to the spring. Another is our eardrums. Our eardrums, whenever we listen, whenever we hear sound, it is constantly forced oscillations. So a lot of examples are there in the everyday life and also in the industries. So large number of examples. So let us see. So here the whole of this topic is divided into 3 different cases. What are these 3 cases? The first is undamped oscillator plus constant force. That means simple harmonic motion and there is a constant force that is being applied. Second is undamped oscillator plus periodic force. Periodic means some harmonic force like F0 cos omega t, something like this. Third case is damped oscillator plus a periodic force. So these are the 3 cases we are going to study. Now as you see, something very interesting here. The first case and the second case, if you compare, here it is undamped oscillator plus periodic force. Now periodic means F0 cos omega t. If omega is 0, then cos omega t is 1. So basically, the second case reduces to the first case if omega is equal to 0. And we will see that. The third case, here actually it is lambda is coming. Sorry, the gamma, the damping constant gamma. So, when the gamma tends to 0 or when gamma is much less than omega 0, then the third case reduces to the second case. We will see all these one by one. So let us take the first case, that is undamped oscillator plus constant force. What happens? So the first step is free body diagram. This is the block, F which is the restoring force and Fc which is the constant force. So let us write the equation of motion. Sigma Fx is equal to Ma minus Kx plus Fc, that is the net force, is equal to Ma mx double dot. That gives rise to mx double dot plus Kx minus Fc is equal to 0. Mx double dot plus K, I am taking K common, x minus Fc by K is equal to 0. Now x minus Fc by K, I put it y. So x double dot is equal to y double dot. So the equation is changed to my double dot plus ky is equal to 0. It is exactly the same equation in terms of y. So we can write y double dot plus k by m is omega 0 square y is equal to 0. Omega 0 is equal to k by m. Now the solution of this equation we know very well, that is y is equal to a cos omega 0 t plus phi. Now in place of y, now I substitute back again, that is x minus fc by k, a cos omega 0 t plus phi. So x is equal to a cos omega 0 t plus phi plus fc by k. Alright. So what we see here over here is that if we add a constant force, then because of that constant force, the whole system shifts by fc by k, that is by a constant. That means you can say the mean position of the simple harmonic motion, it will shift by a constant in the direction of the force. So that is what we see, the effect of the constant force. So this is the simplest of the case. The next one we will see, that undamped oscillator with a periodic force. That means F0 cos omega t. And what will happen? But that is very, very interesting case. Okay, the second case is undamped oscillator with a periodic force. So let us see the free body diagram. In the free body diagram, as usual, there is a restoring force, F, capital F, and there is a periodic force which is acting in the positive x-axis, Ft, given by F0 cos omega dt. Now I have taken omega d as a subscript because it is a driving frequency. Okay? In your book, many books it is not there, but I have taken omega d so that it is clear that it is a driving frequency. So actually what is happening over here, that this is the driving frequency or driving force, along with that the restoring force. So two forces are there. So let us write the Newton's second law, sigma fx is equal to max. Everywhere I want to follow these steps so that you get a habit of writing the equation of motion for any body. So the way is, first write the free body diagram correctly and then algebraic sum of the forces, that is minus kx plus ft is equal to ma, and change a to x double dot, that will give rise to differential equation. So mx double dot plus kx is equal to f0 cos omega dt. So this is my differential equation. Here, this particular force is a function of time, and that is why we have written it on the right hand side. Now we have to find out a solution of this problem, solution of this equation. Before finding out the solution, let us see physically that what actually is happening over here. Here what we find, that suppose say this Ft is not there, then only restoring force, and because of that there is a simple harmonic motion about a mean position. If F is not there, only force is Ft, that will also oscillate the body and that will also create a motion, oscillatory motion. Now, what we have to do, we have to include or add the effects of both of them. That what will happen if both these forces are acting simultaneously. Okay. Now, in general, you see in our everyday life also that when two people meet and they are unknown people, they talk to each other, they speak about their life and they depart. But when they know each other and suppose say their frequency is matching, suppose say you are meeting your friends after a long time, then what happens? The frequency matches and then something builds up. So it may be the sweetheart or anything. Whenever the two people are matching, it is not just two people, but two hearts actually, they join together, they talk together and something built up. We call that love, whatever it is. It happens when the two frequency they match. So anyway, that happens in our everyday life or in our human life. But we have to see that here also similar kind of things happen. When the frequency of these two they match, it gives rise to a phenomena which is known as resonance, and that is a very, very interesting phenomenon. It has a lot of applications as well. Okay, so let us now come back to our mathematics. Mathematically, how we treat this equation? The way to do it is, suppose the solution is x, then what we do, that we keep this as 0. When we keep this as 0, that is mx double dot plus kx is equal to 0. That equation we call as a homogeneous equation, or the solution is homogeneous solution of that part. That is mx double dot plus kx is equal to 0. That is a homogeneous solution, xh. And now we put this f0 cos omega t. Now the whole equation that you form, that is the solution to that, you call that as xp. That means this whole equation, whatever the solution of x is, that satisfies the whole equation, we call that as a particular solution. The general solution is the sum of both of them. So that is how we solve a solution, or an equation of this type, mathematically. Now, how to find out? Suppose say if I want to find out the value of xp, how to do it? One of the best way, or the regular ways of doing it, most of the books they have done it using the complex numbers. Z. You take x as z and then you replace it over here. Now there the advantage is, if you have cos omega dt or sin omega, you can write it in terms of e to the power of I omega t, and that is Euler's equation. It is very easy to differentiate that. So using that, you can quickly solve this. That is a very general method, and you will do it in mathematics, obviously. But here, mathematics is not our goal. Our goal is to understand the physics. So we take a short method, a simple method. We assume xp to be a cos omega dt. Okay. Now, a cos omega dt, why do I choose this? I choose this because you see this side is also omega dt. So here also it should be omega dt. Otherwise they will not match. Fine. So we take x is equal to a cos omega dt and substitute this back into this equation. When you substitute it, you see omega dt, so you will get double differentiated, so you will get omega d square minus n plus k. A cos omega dt is equal to f0 cos omega dt. Cos omega dt cancels out, you get the value of a. So what is the value of a? The value of a is equal to f0 by k minus m omega d square. You can take the m common, so it becomes f0 by m, k by m, omega 0 square. So omega 0 square minus omega d square. Now this quantity is your amplitude. So f0 by m, 1 over omega 0 square minus omega d square, that is your amplitude, cos omega dt, plus, we write plus b cos omega 0 t plus phi. This is the homogeneous solution. Alright, this is the homogeneous solution, and this forms the complete solution or the general solution. We call that a general solution. Okay. Now here we would like to see one thing. As I told you that here if you take omega d as 0, then what will happen? Cos omega dt will be 1. This will be f0 by m omega 0 square. Omega d square is 0. Omega 0 square is k by m, so it will be f0 by k. So it will go back, if you see over here, fc by k. Alright? So it basically you get back the same, whatever the first case is, when there was a constant force. So our solution is matching, is in agreement with the first case. Now here we have one question that comes, and that is a very, very important question. A lot of time we have doubt also with this. The doubt is that this particular solution that we are taking, that is your a cos omega t. Now this is my equation and this is my particular solution I have chosen. If this solution is satisfying this equation, then why not this is the only solution? Why should I add the homogeneous one? Why should I add the homogeneous one? Because this satisfies this whole equation, isn't it? So why should I add, the homogeneous solution? That is the question. See, the reason why should I add this is, if I don't add this, that suppose say this is my only solution, then it cannot define the initial conditions. How? You see, if I take t is equal to 0, initial conditions means t is equal to 0, what is the x? Now t is equal to 0, suppose say I have started with a condition t is equal to 0, x is equal to 0, alright. Now if I put t is equal to 0 over here, then you see that this is, x is this much, but I want to make x is equal to 0, but there is no other option to do it. That is why b cos omega 0 t plus phi, it contains two arbitrary constants. So these arbitrary constants can be set in such a way that, suppose say I want x is equal to 0 over here, so I can do it. I hope the reason is clear to you, that if whatever the initial conditions is, if I want to have the initial conditions, then obviously I need to have other arbitrary constants in the homogeneous solution. Okay. Now again a confusion comes. In the second part of the third part, that is damped oscillator plus periodic force, third part, we are not considering this homogeneous one. Why? We will see that later. There what happens, that there we are interested only in the steady state solution. Steady state solution, why we are interested in? Because there is a damping force, and that damping force finally will cancel this effect, and we are interested in finally that when we are giving a forced oscillation, what is the effect after time, long time t, when it is steady. So there we are not concerned about the initial conditions at all, but here we are concerned about the initial conditions, and that is why inclusion of homogeneous solution is very important. Okay, so now we are approaching the most interesting case, and that is the case of resonance. Okay, what we see over here, that when omega d is varying, when the omega d is approaching omega 0, this term a is becoming infinity. So as omega d approaches omega 0, a tends to infinity. This is what the resonance is. As you see this plot, amplitude is becoming infinity, towards infinity at this resonance. But here in this graph, there is something more interesting which you have to understand. Amplitude is increasing to infinity, that is perfectly fine before omega 0, but after omega 0 we see that amplitude is minus infinity. Okay, there also you can see. What does it mean actually? That after omega 0, amplitude is becoming negative. What does it mean? What it means is like this. The way we can explain is, this is the amplitude which is becoming negative. Instead of writing amplitude negative, what we can write, the phase term cos omega dt plus pi. Cos theta plus pi. So that is also negative. Now even if I write that cos omega dt plus pi, what is its significance? Its significance is that before omega 0, till omega 0, my force and the displacement, they are in phase. After omega 0, the force and the displacement, they are out of phase by pi. Phase change of pi radians occurs through resonance. That is, a significant thing. they are out of phase by pi. Now what does it mean? Pi phase, pi by 2 phase, out of phase by pi means if you consider a circle, then a particle moving in a circle. So out of phase by pi means it is both are maximum but they are in the opposite direction. Crest, trough and all this. So that is what it happens over here. So this is a very, very interesting case of resonance. And amplitude rises very high when driving frequency is approaching the natural frequency omega g. So that we know actually, and you have also studied resonance before. Now there are a lot of examples of resonance in our everyday life, in our instruments, in our devices. One of the examples that we know is radio tuner circuit. In the radio tuner circuit, when you tune the radio to a particular station, the natural frequency of that station matches with the tuner circuit and the amplification, the amplitude rises up. So you can hear that sound. And then, by amplifying it, basically we listen. So that is a very, very important device and an example, applied example of resonance. Another example, many times people quote, and that example is of that at Tacoma Bridge. There was a bridge named by Tacoma Narrows Bridge in Washington in 1940. What happened that after that bridge was opened, after say 4 months or so, one day there was a strong wind, gust of wind, and because of that it was vibrating. And vibrating very large, vibration increased finally, and finally it shattered. So the people in physics many times, they explain this phenomena saying that the bridge was vibrating at its natural frequency. Obviously everything will vibrate at natural frequency. The wind also have the gust of wind that came, though it vortices and puffs, whatever it was happening, it loosened the screw of the bridge, and then finally that frequency matched with the frequency, natural frequency of the bridge. And that is how the bridge started vibrating very large and finally it collapsed. But then people argue that it is not the case, because if you find out the natural frequency of the bridge, it is something very different and it is not the same as that of the blowing air at that time. But anyway, you must see this, because in the internet, I was thinking to put that video over here, but there is a copyright violation. So you better see that video, and also the explanation, counter arguments, all those things are there in the net. It is a very interesting study. Another video you must see, that of Professor Walter Lewin, and he is an MIT professor. He was actually, and he had very good number of videos, and everything he demonstrated in the class. So he had done a experiment on a wine glass, and first of all he was showing that how you can produce sound using your fingers, again natural frequency. Then after that, what he had shown, that there was a sound box where the sound was coming, and it was matching with the natural frequency of the glass. So the glass started vibrating, and finally that glass broke. So very, very interesting experiment. You must watch that video by Walter Lewin, where he has demonstrated the whole experiment in the class itself. And you may see a lot of other examples in our everyday life where this important resonance actually builds up, the devices and many other places. So that is about about your undamped oscillator with the periodic force. Now, in the third case, we will go to damped oscillator plus periodic force, where all the forces are working together. That means your restoring force, the damping force, as well as the forced vibration. That is the force, that is F0 cos omega t. Now we will go to that particular case. So now we will go to the last part of the three, and that is the most interesting part. That is a damped oscillator plus periodic force. So we have done undamped oscillator plus periodic force. So now damped oscillator plus periodic force. And there we will see that the damping constant gamma, when it becomes 0, it will approach the case 2. Okay, so first let us see the free body diagram. In the free body diagram, we have all the forces present over here. The force capital F, which is the restoring force, small f, which is your viscous drag, damping force, frictional force, and Ft, which is the periodic force. F is equal to minus kx, small f minus bv, Ft is equal to f0 cos omega dt. Now let us write the Newton's law. Sigma fx is equal to ma minus kx minus bv plus f0 cos omega dt is equal to mx double dot. So finally we get mx double dot plus bx dot plus kx is equal to f0 cos omega dt. Again, you know, the temporal, because of the temporal dependence, we have separated this f0 cos omega dt. So finally, we can write this equation as you know, x double dot plus gamma x dot plus omega 0 square x is equal to f0 by m cos omega dt. Just dividing by m and writing b by m as gamma and k by m as omega 0 square x. So this is my equation, or the differential equation, for the damped oscillator with a periodic force. Alright. After this, we have to look for the solution. What will be the solution? General solution will be x is equal to, again as we have studied earlier, x homogeneous plus x particular. Now, the homogeneous equation is, this part of the equation is equal to 0. Now that we have already seen that that is the, when we studied the damping oscillation, x homogeneous is e to the power of minus gamma by 2t, or we can write, you know, a also here, cos omega 1 t plus phi. A e to the power of minus gamma by 2t cos omega 1 t plus phi. Plus xp, that is plus x particular, that is time. Now x particular is when the whole equation is there along with this f0 by m cos omega t. So whole equation, the complete equation, the solution of x is your x particular. Now here we have to understand very important point. Important point is that this xt what we are writing over here, this is the general solution, where both homogeneous and particular solution is there. But with time, with certain time, what will happen, that e to the power of minus gamma by 2t, it will die out with time. So it will approach 0 as time progresses. After that, what remains is x particular. So presently in our case, we are only interested about the what remains after the initial time, that means after this becomes 0. We call that as a steady state solution. So someplace we have, you know, done the full solution like the earlier case. Here we are interested in the steady state solution because we are interested in force. The force is acting as a periodic force. When some periodic force is working and continuously working, we want to see that what is the behavior of the system after a time t, a good amount of time t, not initially. So initially there will be some damping and that will die out. But if I am interested to just to know about after time t for a very short amount of time, we have to consider both these solutions. But presently we are not interested. We are interested, since we are giving a force, f0 cos omega dt, we would like to see the steady state solution. That after time t, what actually is the steady state solution. I hope it is clear to you. So steady state solution xt is equal to x particular. Fine. Now, what will be the x particular? Let us see. X particular will be a cos omega dt. Again, the same principle, same logic. Since the right hand side is cos omega dt, we have chosen a cos omega dt. But here there is a problem. And what is the problem is that when you are writing this, here in the earlier case it was not there. Here as you see, x double dot is perfectly fine. The cos omega dt will come back. But gamma x dot, here you will get a sine function, sine omega t. So your equation will contain both cos as well as sine. Here you have cos, so you are landed up with difficulty. So what to do? So we will choose x particular is b cos omega dt plus c sine omega dt. That means containing both cos and sine terms. And substitute back over here and find out the value of b and c. Now this is the way most of the books have done. What Kleppner does is little bit different, almost the same. He takes up xt as a cos omega dt plus phi. He assumes because it is both are same, both will contain cos a cos b plus sin a sin b whatever. So both way you contain both these formulas will contain cos and sine terms. So he has taken this. Now you substitute it back again, and after substituting it, the value of a you will get is f0 by m omega 0 square minus omega d square whole square plus gamma square omega d square root over. So this root over is over the whole expression, alright, whole expression. And tan phi is equal to gamma omega d square minus omega 0 square. Alright? Okay. Now here also we have to understand few important things. First of all, if you substitute only the first part, what you will get, the solution you will get, this particular solution will be minus over here. But at that time, tan phi, you will be get omega 0 square minus omega d square. But if you can write this way also, that is omega d plus phi. But finally, when you are writing tan phi, it is omega d square minus omega 0 square. Now, this particular expression, that is tan phi, is throughout negative. If you see the plot is there in the book, I have not written over here. If you see the plot is totally negative. But there, one thing that you have to remember, that sometimes you may feel that if omega 0 is less than omega d, what will happen? All these confusions may come. So it is better you look up the book. So there you will find one identity you have to use, that tan pi minus theta is tan theta minus tan theta. So tan theta minus pi is tan theta. So you have to use that, and after using it you will see that you are getting the tan phi as throughout negative. Okay. I will tell you more about this. But before that, if you are getting omega t minus phi, or it is negative, what does it mean? It means that the displacement here is lagging the force. Our force is f0 cos omega dt, and displacement is cos omega dt minus phi. So in some of the books you will see that there is a plot of both the force as well as the displacement, and displacement lags the force by the phase phi. That means it lags, the displacement lags by delta t. Delta t will be equal to delta phi by omega. Alright. So there is a lag. That means if there is a damping present, you are giving a force, the displacement the resultant displacement will be delayed. So there is a lag between the force and the displacement. That is what the significance of the negative sign over here is. Okay. What more we can learn from here? What more we can learn from here is that suppose say our gamma is 0. Now if gamma is 0, then you will see that it is f0 by n omega 0 square minus omega d square. So it is just the the previous one. Okay. So yeah. So it is that expression. So as you see, if omega gamma is 0, you are getting that expression f0 by n 1 over omega 0 square minus omega t square. Gamma, if gamma is 0, so you are getting back that. If omega d is 0, then what, this term goes away. This term is also 0. f0 by n omega 0 square. Omega 0 square is k by n. So you get f0 by k. That is the first case. Alright. If that is a constant force, that means omega d 0 means it is not a periodic force, but it is a constant force. So you are getting back that same equation. That is the first one. Now you may think that if gamma is present, suppose say, if gamma is present, I am not able to accommodate that solution. Like if gamma is present and omega d is 0, suppose say, omega d is 0, and if gamma is present, this particular solution, I am not getting back this solution, that damping one. It is because that presently we are only following the steady state solution. And that is why in the steady state solution, when you see this A, as you see, its A is all fixed. There are no arbitrary constants here. Arbitrary constants you get only when you include the transient terms which was there, so that you can handle the initial conditions. That was there in this equation. This equation we have that because it was including right from the beginning. But here we are not including right from the beginning. We are including the steady state. In the steady state, whatever is my initial condition, that doesn't matter. I have forgotten about my initial conditions. So initial condition will not come over here. It is only the steady state solution. So from the steady state solution that we are considering, that whether it is gamma initially, so the one that we have considered, this one, we will not get back into that. I hope that is clear to you, that why it is not able to handle this equation when gamma is present and omega d is actually omega d is 0. That because we are doing the steady state solution, we are not doing the complete solution. So these are the most of the important points that we must know. Now regarding the phase of this we will see in the next slide here. If you see that the diagram, the plot of amplitude versus when the damping is very low and the damping is high. Now what Klippner has done, this is from the Klippner only I have taken, he has written gamma by omega 0. Damping low means what? Damping low means gamma compared to omega 0 is very less. That is the damping low. So gamma by omega 0 much less than 1. That means gamma is much less than omega 0. Gamma is a damping term and omega 0 is an oscillatory term. So compared to omega 0, gamma is very small. That is what the gamma low means. Otherwise, just if I say low, it doesn't mean it actually. So gamma by omega 0 much less than 1. Okay. So here, as you see, that this is the plot, and this is the plot when gamma by omega 0 is approximately equal to 1. That means near about 1. That means gamma is of the order of omega 0. In that case, the case is a little bit different. And this particular example we will see from here, we will understand here. Now let us see the first case. What happens that this particular A amplitude, when will it be maximum? So here very interesting thing happens. It is not maximum when omega d is omega 0 like the case before, like the case of resonance before. Here this particular denominator, when this will be minimum, only then A will be maximum. So we have to find out that when this denominator will be minimum. Now here as you see that the variable is omega d. So we have to differentiate this with respect to omega d and put that is equal to 0. That will give me the minimum value of omega d. Let us do that. That is known as resonant frequency. Now here, when A is maximum, the minima of the denominator. So d omega d of omega 0 square minus omega d square whole square plus gamma square omega d square is equal to 0. Straightforward maxima minima problem. Now, if you do it, you will get this expression. From here, omega d square is equal to omega 0 square minus gamma square by 2, not gamma square by 4, gamma square by 2 is equal to omega 0 square resonance. So this is my resonance frequency. So my resonance frequency in case of damped harmonic oscillator, when there is a periodic force, is not omega 0 but little less than omega 0. That is omega 0 square minus gamma square by 2. And that is what we will see in this particular graph. Okay. Now, before we go to the graph, let me discuss the light damping case. That means when the gamma is very small. That means again, gamma small means gamma by omega 0 is much less than 1. At that time, when the gamma is much less than 1, omega d is approximately equal to omega 0. So omega d is approximately equal to omega 0, that is the omega resonance. And now what will be the amplitude? In order to calculate the amplitude for low damping, that means light damping or very low damping, that is very low damping, you substitute this value of omega d over here and neglect the higher order terms. That means neglect gamma 4 and higher order terms, keeping the lower order terms of gamma, because we cannot neglect gamma completely. That will be, the previous case. So you have to keep the lower order terms, the higher terms you have to neglect. From there, you will find that the amplitude for the low damping case or light damping case is f0 by m omega naught gamma. This is the amplitude that you will get for the low damping case. Now, low damping case is this one, basically, light damping or low damping. That is gamma by omega 0 much less than 1. This is the low damping case. As you see, very low. So here, the graph looks like a Lorentzian. And the maximum amplitude is at omega 0, which is your omega resonance. So this is when gamma is much less than omega 0. Now, when there is higher damping, that means gamma by omega 0 or gamma is somewhat near about omega 0. At that time, this is the plot of A. As you see over here, that omega 0 is somewhere here, but omega r, which is actually resonant frequency, coming out from this expression, omega 0 square minus gamma square by 2 is falling somewhere before that. Alright? So this is a very important case, that in case of damping, when there is a periodic force is there, the resonant frequency is not at omega 0, but it's something before that. That is omega 0 square minus gamma square by 2. And from here, some problems also may be framed for your exam. Okay. Now, for these two plots, I request you to go back to your book, because you should also read your book, Klipner, it gives you the phase diagram. That means how this tan phi changes. Alright? How this tan phi changes. So you will see the plot of tan phi as well. For this particular case, when gamma is much less than omega naught, you will see that the phi changes, as we have discussed in the case before. The phase angle phi abruptly changes from 0 to minus pi, and that is what we have seen before. So the phase suddenly changes. But in this case, if you see, the phase changes, but it is gradual because of the damping. So when there is a damping, suddenly, when you are giving a f0 cos omega t, the system responds slowly. Okay. So what you see, the change of this gamma, so change of this phase phi is gradual, it is not abrupt. First it is 0 for low omega 0, and at omega 0 it is pi by 2, it is minus pi by 2, and for higher omega it is actually minus pi, and there is a gradual change because of the damping term. Now you may think that what is the concept of this minus pi by 2 phase, minus phase. You see, we have studied minus pi by 2 actually means, in the waves, when we studied waves, minus pi by 2 means that when one is maximum, other is minimum. As you can remember, the circle oscillating, a circle body moving in a circle, and we take the projections of that circle, which is the simple harmonic motion. So pi by 2 means the body is somewhere here, and you take that means at the origin basically, and the 0 is at the outer end when it starts. So when something is 0 means it is actually maximum, pi by 2 it is minimum. The same thing is minimum. So the phase angle, you can think in that line, that when a particle is moving in a circle and taking the projections. When it is minus pi, that means the difference, one is minus pi, that means both are at extreme end, but the one is opposite of the other. Maybe the direction of one is opposite to the other, or whatever, it depends upon the case to case, but both are maximum, like crest and trough. So both are maximum, but one is positive, other is negative. One is decreasing, other is increasing. So, but both are maximum. That is what minus pi means. So please see your book, and I hope you will appreciate that how that phase is changing. I don't want to include everything over here, otherwise it will be too lengthy. So just go to the book and see that how the phase is changing. So phase actually determines the relation between the force and the displacement. The force and the displacement. How they are changing one from the other. That means how delayed they are, or what is the direction, all these things. After this topic, so we have completed now almost all the relevant quantities that we are willing to study. The next topic is energy and power. Now, I don't want to go into the details of it, writing all the detailed expression, because unnecessary, because once you know the terms like F and X, you can calculate yourself. So as you see, F is F0 cos omega dt, and Xt also you know. From these two, you can calculate any quantity. Like energy, kinetic energy plus potential energy is equal to half mv square plus half kx square. Now you know V, because the moment you know X, you can calculate V. Moment you your potential energy X you already know. From there you can find out the total energy. Now if you want to find out usually it is people write it in terms of average energy per cycle. In that case, if you take the average, the sine square term and cos square term, the average of the sine square and the cos square over a cycle is half. So using that, you will get this expression. But you need not memorize this expression, but this is the expression that you get using these relations. That is about the energy. About the power absorption, see, suppose say we state steady state. Then in steady state, what will happen? The force actually is giving some energy. So force is supplying energy, but energy is getting lost by dissipation. Okay? So force is giving energy, energy is getting dissipated. So in the steady state condition, whatever my force is giving energy to the system, the same energy is getting lost. And that is how it becomes a steady state. So if you calculate the power absorption by the force, that is F into velocity. Again, you can calculate the average power. Power dissipated. Power dissipated is, by that drag force. So minus Bv times velocity, it is minus gamma mv square. Again, you can find out the average. Both these average, it should be same. You can calculate and see. So this is all about energy and power. You can I don't want to write all the detailed expressions, because the most important thing is you must understand the fundamentals. The moment you understand the fundamentals, you can calculate everything. One point I have left out, that is the Q. Q is the same, but there is another way of calculating Q. The way is, what is Q? Q, we have seen that expression for Q for low damping case is omega 0 by gamma. And often, we write omega 0 by gamma. Now, omega 0 from this graph, you can see. If you plot a graph, either of, energy or of power, what you will find that the graph looks exactly like this, because amplitude square it will be obviously proportional to. So, this will look exactly like this for low damping case. And presently, that is what we consider most of the time. Low damping, very low damping. It will be a Lorentzian function, Lorentzian graph. Now, here you see at omega is equal to omega 0, omega d is equal to omega 0, this is maximum. Okay? Now, if you take somewhere here where the half of the maximum, wherever the amplitude becomes half, and if you take the width of this, so it will be basically, if you draw a line over here, one point will be omega 0 plus gamma by 2, another one will be omega 0 minus gamma by 2. So the width of that, where the amplitude becomes half, will be gamma. And that we call in technical terms FWH, full width at half maximum. Okay, full width at FWHM, full width at half maximum. So there you get the gamma. Alright. I hope you are following it. Whatever is the half, wherever the amplitude, here amplitude, but there it will be energy or power, whatever it is. Wherever there is half of it, from there, you can calculate the width of that, will give you the frequency width. So, omega 0 divided by gamma will be omega 0, that is your resonant frequency, divided by the frequency width at half maximum. So, that will give you the Q. You can just go to the book and you can study about the value of Q. So, this is all actually we have to read about our forced harmonic oscillator. So, so as I hope now you appreciate that the first case, the second case, when omega d is 0, we are getting the first case. From here, when gamma is 0, we are getting the second case. Though in the second case, both the transient solution and the other solution that we are getting, both of them are included in the general solution. So that becomes a complete solution. But here we are taking only the steady state solution. I hope I am clear with whatever I have told you, and go through it and also go through the book. The problems, I am trying to formulate some problems, and yesterday I have taken a video of one child in the children's park, and so I have given you two videos. I have taken two videos actually. One when he is normally swinging, and slowly, that is dying out. The other one when he is giving a force, so that is a forced oscillator. So I have assumed that it is f0 cos omega t, and with that assumption, I have formulated a small problem. But I will try to get some more problems so that it gives you a feeling that what actually is a forced oscillator or forced damped oscillator with periodic force. So okay, thank you very much. So I was looking for some questions. So finally I got, there are a lot of questions, but some small questions which can clear our doubts and concepts. So two objective and one normal questions. Let us see. A weakly damped harmonic oscillator of frequency M1, N1 is driven by an external periodic force of frequency N2. When the steady state is reached, the frequency of the oscillator is, the first answer is N1, N2, half N1 plus N2 and root over N1 plus N2. So which one will be the correct answer? Think about it. See, in this periodic damped oscillator, the driver is, trying to oscillate. So, in the steady state situation, when the driver, in the steady state situation, the driver and the oscillator, they will both oscillate with the same frequency. Because here the driver wants the oscillator to resonate, or not resonate, but to go along with that driver. So both will have the same frequency, but the amplitude is not the same. In case of amplitude, what happens? When the driving frequency is low, amplitude is low, because it is doing very slowly. The amplitude cannot pick up. When the driving frequency is too high, even then amplitude is low. And if you see the mathematical expressions, the expression for amplitude that we have derived, f0 by m divided by root over omega 0 square minus omega d square whole square plus gamma square omega d square root over of that. There also, if you see, if omega d is large, that means driving frequency is very large, the A is very less. And the reason is that it is so oscillating so fast, the driving frequency, that the oscillator is unable to pick up. The moment it takes up the amplitude, again the other side it comes. So when the driving frequency is very fast, the amplitude cannot pick up. It is confused. The oscillator is confused. Alright? So the amplitude at high frequency is also low, at low frequency is also low. Only the case is when there is a resonance, that means omega d is approximately equal to omega 0, during that time the amplitude is very high. But the driving frequency of the oscillator as well as the driver, because the driver is trying to drive in the steady state situation. If you read the first paragraph in the book Resnick Halliday Cream, very nicely he has written that. Very nice book. It is one of the best books in physics. And so our answer will be by external N2. So answer will be N2. When a steady state is reached, the frequency of the oscillator is N2. Here, let me tell you, elaborate a little bit more. You know, we have three important terms. One is the amplitude, the second is the frequency, and third is the phase. So, the frequency is always the same, steady state situation. The frequency of the driving force or the driver is same as the frequency of the oscillator. Amplitude, initially it is low for low omega d, then finally it rises up, it goes very high at the time of resonance, and then slowly it will decrease with higher omega d. And third thing is the phase. The phase tells us about the relation between the time lag between the force and the displacement. That we have already discussed. So these are the three important quantities that we have studied. A very weakly damped harmonic oscillator acted upon by an external periodic force is executing simple harmonic motion in steady state. Weakly damped harmonic oscillator. The phase of the oscillator with respect to that of the driving force at resonance is. That also we have discussed. That during the time of resonance, as we have seen, for a weakly damped or not so weakly damped, if it is totally undamped, then the phase changes from 0 to minus pi in our case. But otherwise, it goes through minus pi by 2. So at resonance, basically it is minus pi by 2. So it is pi by 2 is given, so we can take this answer. It goes at pi by 2 at resonance. Okay, so these are the two objectives, but this question is the most important one that you must be very careful. The lesson that it teaches, because this is very, very common question, that the frequency of the driver is the same as the frequency of the oscillator in the steady state situation, but amplitude is not. Okay. So let us see the next question, which is a very, very nice question. When a block of mass 2 kg is hung from a string, it stretches by 2.5 centimeter. The top end of the spring oscillates up and down with amplitude of 2 millimeter. The Q value of this system is 50. What is the omega 0 for this system? Find the resonance frequency, find the amplitude at resonance frequency or omega 0, whatever it is. Now this is a very, very nice question, and I hope you understand the question. The question is that there is a spring, unstretched. When I put a mass under it, then it gets stretched by delta x. Now somebody takes up the other end and starts oscillating with simple harmonic motion. With simple harmonic motion, it is oscillating, the top end part. Now the question is omega 0, resonant frequency, and the amplitude of at the resonant frequency. Now this problem is taken from a very old book, but very nice book, very good book, and that is Vibrations and Waves by A.P. French, 1971 edition. Now, as I told you a long time back that when I first started my career in BITS Pilani, long time back in 1999, that was the book that was being followed, for the first year students. So, Vibrations and Waves, very nice book, but it is a tough book. Now, this particular problem, as you see, the same problem, if you see the video of Walter Lewin, the same experiment he has done it horizontally. That means horizontally there is a block connected by a spring, and then there is a oscillator which basically oscillates. It is a very, very beautiful experiment, and you must see that during the time of resonant frequency, the oscillation is maximum. So right in the class, he shows that. So it is a very nice experiment to see. exactly the same thing is happening over here in the vertical plane. Now, how to solve this problem? First of all, what is omega 0 for this system? Very easy. Because your delta x is given to you, so you can calculate omega 0. I leave it to you because I will not give you the full solution. First of all, I would like you to do it. Okay? So from delta x, how you can find k, and then how you can find omega 0. Find the resonance frequency. Alright. So there we have to find out the value of gamma. Now gamma you can calculate because the Q value is system is given and Q is equal to omega 0 by gamma, so you can find out that. The third problem here, and that is what we have to find out. For that, we have to see the expression of A contains F0. Now how to calculate F0? Because here I am applying a force and I am executing a simple harmonic motion. So obviously the force is F0 cos omega t. But my amplitude is given. Suppose say whatever the amplitude is. Say here it is A. Amplitude is given A. Alright. Here also amplitude is given. That oscillates up and down with amplitude of 2 mm. Okay. So I have just taken A. So it is oscillating with amplitude A. What is the corresponding force for that? Now, well, one way quickly one can go into the conclusion that yes, it is a simple harmonic motion. So the acceleration you know, and acceleration is mass times acceleration is a force. But here we are applying over here. So there is no mass at that point. That is a problem. So m into a you cannot do it. So what you have to do, it is a little bit typical, but one has to think. What one has to do, that you have to take the block, okay, and in the block basically you have to apply the force. So all the forces you have to show it on the block. If you put the force over here, though we are putting the force over here, but finally we cannot solve it. We cannot write the equation because mass of this point suddenly we cannot write. So we have to see what are the forces which are acting on the block. And then you can write sigma fx or fy whatever is equal to ma, and finally you will get all the quantities. So I would like you to first try that, and then I will show you the solution. One suggestion that I would like to give, what you do, that suppose say this block is oscillating. Now once the block is stabilized, that means it is hanging here, obviously I have to hold it by something, so that it is I am holding it. Now another force that is I am giving it, that is your F0 cos omega t. Okay. So the way we can think of it, that suppose say the block is at time t at some arbitrary position over here. Suppose say this is position P. Alright, position P. Or position P I can write over here. This is position P. At position P the block is over here. Now this position, the displacement, this is the main position. From here the displacement suppose say is x. And at that time this part of the spring is somewhere here, that is x prime. So